Liebherr Performance, Innovations in Gear Manufacturing. So let's get started. This is the VDW Web-Symposia for USA and Canada, and my name is Scott Yoders. I'm responsible for sales of Liebherr gear machines for all of North America, USA, Canada, and Mexico. And just by way of introduction of my person, I'm a mechanical engineer from Penn State, and I've been working for Liebherr since the year 2007. And prior to joining Liebherr, I was in gear manufacturing myself. I made gears as an engineer in automotive for about 10 years. This is the agenda for today. Give you a brief company background. I will show you about our solutions for machine tools. And then the three interesting topics or innovations we've worked on, which might be interesting to you, is e-mobility, our skiving process, chamfering of gear teeth, and then I'll summarize with an outlook. Okay, the company background. Liebherr is a family-owned company started by this man, Mr. Hans Liebherr. It was started in 1949, and he had the idea for a crane which could be built quickly on site. Yes, of course, in those days, from after the war, his product did quite well in construction equipment around Europe. And today it's still a family-owned company. Mr. Hans Liebherr passed away in the year 1991, and his son and daughter, shown on the right on this picture, ran the different divisions of Liebherr. And today, since about the last 6 or 7 years, we are in the third generation of ownership. So the grandchildren of Hans Liebherr now run our company. And specifically for our group, it's Mrs. Roof, and she's shown right in the middle of this picture. So yes, it's a family-owned company, completely privately owned, but one of the largest privately owned companies in the world, which is wholly family-owned. There are no other shareholders but the Liebherr family. And many people, especially Europeans, know our products. I would say we're most known like the Caterpillar of Europe. We make a lot of construction equipment, not just cranes, but also earth-moving equipment, bulldozers, mobile cranes, excavators. That's probably, yes, the most recognizable product, but we make other things too, like refrigerators, rail transportation systems, builder, so he made some hotels too, and also us, gear machine tools, and that's what we'll focus on today. But yeah, the different businesses more or less run themselves. We have a high level of independence. Hans Liebherr had the philosophy, think for yourself, do it for yourself, no long decisions, just go for it. So that's how we more or less operate our businesses. Excellent company to work for. Speaking from my experience, we have about 14 billion annually in sales, US dollars, since last year, and about 55,000 employees worldwide. So it's a very large privately owned company. Here you can see the turnover by product groups, and the highlighted in blue section is us, our division of gear machines. And it's about 2% of the company. So we're very tiny in comparison to Liebherr Group. But for a machine tool builder, we're very large. We've got about 1,600 employees worldwide. And in Germany, yes, I would say one of the largest machine tool factories in the country. And we produce machine tools, metrology, and automation systems, which I will go into now. You saw from the slides, we are a very small part of the Liebherr Group. However, we're really at the foundation or beginnings of the company. When Hans Liebherr started building cranes, he needed gears, specifically the large diameter slewing bearings. And gear machines, there was one manufacturer in Germany. It had a long delivery time and was expensive, so he said, must be a market. So we started building gear machines in the year 1952. We produce all of those machines today in our factory in Kempten, Germany. And Kempten's in the Allgäu, about, let's say, an hour and a half or 2 hours southwest of Munich on the border with Austria. And we're also producing our automation systems, which we use for our own gear machines, but also sell externally to other machine tool builders. And we had an expansion in the year 2009. And yeah, we can produce on annual about 300 machines is our capacity. Only gear cutting machines. So our products are only, we don't do any turning or milling or general purpose machining. It's all specific to gears, hubbing, shaping, skiving, gear grinding, gear chamfering, and gear inspection or metrology. We also produce automation systems. You can see here in the picture a gantry system that's pretty typical from Liebherr, but we also make our automation for our own machine tools too. These are the processes. These are what they look like. Not so sure how familiar the audience is with gear cutting, but it's generally done on the generating principle, and I'll get to that in a minute. But we make hobbing machines, which are the LC, shaping LS, grinding LG, skiving LK, and deburring or chamfering LD. So those are the 5 technologies of machine tools we produce. Anywhere for gears which can fit in your hand, 50 millimeter diameter, all the way up to the largest gears in the world, over 16 meter diameter workpieces. So anybody who makes a gear is our customer. And these are the generating processes, as I alluded to. Unlike other general purpose machining, we're a little bit complex in that, yes, you define a cutting process with cutting speed, feed rate, and depth of cut to define the metal removal rate. That's how you can compare any process. But sometimes we have 2 feed rates, like in the case of shaping, or 2 cutting speeds, like in the case of skiving, or let's say a changing depth of cut. So our chip thickness is changing as the workpiece rotates in harmony with the tool. So that's what makes gear cutting a little bit different than other machining, and that's what we specialize in. And our customers in North America, since this is a North American audience, our passenger cars for our smallest machines, and tier 1, tier 2 suppliers. Let's say the gears like we make for Liebherr ourselves, like the Caterpillar, John Deere, people like this are in this size range. Off-highway ag, sometimes large aerospace components are in our platform 3 machine tools, up to 1.6 meter workpiece diameters for gears. And then mining, yeah, we also make these gears for ourselves, but we sell these machines externally too, for earth moving equipment, big shovels, big dragline shovels. And yes, I mentioned it earlier, we produce the largest machine tools for gears in the world, up to 16 meter workpiece diameters. And I alluded to also not just gear cutting, but gear inspection or metrology. We are just over 2 years of purchasing another German machine tool company's division of gear inspection machines. So these machines formerly were made in Franken at a company well known for CMMs there, and we purchased their gear metrology division. So the WGT machines are the way we inspect the part by rotating the workpiece on the base circle. And I alluded to automation. We also make automation. So we do these gantry loading systems, robot loading systems, pallet handling systems for workpieces with long machining times. Maybe they only make 1 or 2 parts and change over. The machine is capable to change over the machine tool as well. And robot solutions like random bin picking, we also are very familiar with. And then when I get to some of the, let's say, special topics, what we're working on in gear manufacturing, and specifically the innovations, which could be interesting to you guys. E-mobility is obviously a topic on everyone's mind, not just in the machine tool industry, but all over the world in automotive production, bicycle production. So typically we have some special applications for gears in these gearboxes. High RPM, need high efficiency. So oftentimes we don't find bevel gears, we find parallel axis gears for efficiency. Lightweight construction, especially on the smaller applications, passenger cars even, where you try to reduce the face width of the gear to get more power through a smaller density. And it's typically gears are needed to be ground for e-drives almost always. And why? Because the NVH is so important on e-drive gears. So increased quality demands compared to other passenger car applications. Like in North America, we're very used to automatic transmissions, but manual gearboxes, these gears are, let's say, on a different scale in terms of quality. And I guess the easiest way to describe that is in working with myself, having worked with some of these people on their gear manufacturing, the rotational speeds and let's say the no load conditions are where the noise is most important. And normally all the modifications which we put on gear teeth, which are shown on the left here, those are done for underloaded conditions of the gear tooth. So what we find in e-drive is they have a lot of noise under low load or no load. So when the gear is coasting in the transmission, and that makes it extremely challenging because there's not really corrections you can put under the flank. It's all manufacturing error. So manufacturing error, improving the manufacturing process is critical. Here are some of the gear geometry we can make for those loaded conditions, and those are also very important to the e-drive manufacturers. And I like to focus on a couple developments Liebherr has done. One of which is twist correction. This is an old patent from Liebherr from the year 1989, where we, along the grinding wheel, and shown in the bottom left-hand corner is a grinding wheel, and if I make this my workpiece and this my grinding tool, where we move from point A on the tool to point B in this direction. So we shift over the length of the cutter or the tool, and we make a pressure angle correction along the basic rack profile of the grinding worm. Again, an old idea from Liebherr. We did this back in the 80s, early 90s, where we did CBN wheel grinding, where we didn't change diameters of the cutting tool, in this case, a grinding worm. So we make those corrections from point A to point B on the workpiece, point A to point B on the tool, and we can take out any so-called twist. So yeah, let's go back quickly to the diagram. Twist means the designer is looking in the middle of the tooth on both the lead and profile direction, and that's the ideal condition. Then if you make these center distance changes while grinding, it causes an unnatural or a natural twist to occur in the tooth. So basically this idea we had way back then was to take that twist out of the gear tooth to make it the perfect geometry as you see in the middle on the ends of the teeth. Yes, similarly, we've come up with a so-called generated end relief. And this we did in profile grinding for years, where you put the grinding disc through the workpiece, and then you chop off the tip, you chop off the root, and you can carry more load. Because on a helical gear, as shown here, all the loading is in this zone. Typically, an end relief would be along the face width of the gear. So what we've done is applied this old idea to modern generating grinding. And with this generated end relief, you can reduce the face width of the gear, so you can make the gear thinner and carry the same loading. This is a super important topic for, of course, e-drive applications where lightweight is really necessary sometimes. So here we reduced some, yes, 12 millimeters on the workpiece width, and then you can really carry the same loading with this end relief. And here you can see a little video of the process, how it works. Of course, the grinding oil is switched off, and you can show the grinding process where we make this generated end relief correction. And here you can see in the middle of the screen, topography of what the workpiece looks like. So we have that end relief on the section. We coupled this with another, let's say, innovation from Liebherr, which is polishing. Also was an old patent from Liebherr in the early 1990s, where back then we used the rawhide worm. Nowadays we use, you can see this green polymer grinding tool, where we basically, yes, we can super finish the gear teeth to extreme low RZ values, where we keep the pockets in the gear teeth, oil pockets, but the top has a bright shiny surface like a mirror, so that really you can have a better efficiency in your gearbox or lower viscosity oil. Yeah, so that's what the process looks like running for the generating grinding with the GER and the polishing. And then I already mentioned it. This is a CBN tool, cubic boron nitride. This is how we started with grinding back in the late 80s. Back then it was a really, let's say, cost-effective way to make gears because you could go for higher feed rates and cutting speeds than you could with aluminum oxide or corundum tool. This almost went away in the early 2000s because of the development in the corundum tool technology. They used these microcrystalline sintered gel ceramic corundum wheels, which basically, and even us, we got rid of the CBN as really a mass production alternative. But we think it comes back a little bit because I showed these tolerances, how e-drive applications are much reduced compared to manual and automatic gearboxes. So we think this process stability and all of these complex corrections like GER and twist free, there is maybe a place for adjustable free CBN to come back in e-drive applications. Yes, and we have many other developments for generating grinding for e-drives. The adjustable free CBN I mentioned, the fine grinding or polishing. We can also go for asymmetric gears so that we can optimize that coast flank versus drive flank. So we think that has really some future potential in e-applications. And collision critical. Oftentimes we use a very long diameter worm or small diameter worm, long length. So that if you have shoulder gear work where some of these e-drive applications are in gears, then we can really go for the smallest diameter tools on the market at Liebherr for generating grinding. We call all of that our deviation-free topological gear grinding, and we find it to be, yes, really applicable to the new challenges given to us by the e-mobility applications. Another process which you maybe see if you look to any machine tool show or trade fair, is skiving. Skiving is, let's say, the newest gear process. And what I want to highlight is what we really do at Liebherr, which is we call it skiving cubed. We control not just the machine tool design, but also the cutting tool design where we manufacture ourselves, and also the process. This is extremely critical to the skiving process. Maybe you just have a quick look on what we can do with our skiving machine. Not only can we skive, but we can also do, let's say, light duty turning, also drilling some holes, also do some gear inspection. So our skiving machine is built not just for the gear cutting process, predominantly the gear cutting process, but we can do some other alternative applications, even, let's say, probing or inspection on the piece. And this is what skiving looks like. I will run the video here. Again, with the cutting tool, for the cutting fluid. And you can see it operates on a cross axis. So the workpiece is typically an internal gear for skiving, and the tool has a cross axis to the center line of the workpiece. And then I go back to my favorite slide from the generating of gears to show this skiving process, because many people think, yes, it's absolute newest process available for making a gear, and that's somehow true. But we should remember hobbing was invented in the late 1800s, shaping in the also late 1800s, and skiving was invented in the year 1908. So from that perspective, yes, it's the newest one, but it's been around a long time. And why hasn't it worked, or did we only until recently, let's say the mid 2000s, start seeing skiving as a real industrial stable process, is due to this negative rake angle. So if you look at the hob cutting, there you can grind into the tool a positive rake angle, and it works with different cutting speeds and feed rates if the same tool. Same with shaping. You can grind a positive rake angle onto the face of the cutting tool. Skiving, you take basically what looks like a shaper cutter. It's not, but it looks like. You tilt it on the cross axis angle, and automatically you're plunging a negative rake angle into the workpiece. And therefore, you need an extreme high stiffness in the machine tool, and you need an extremely intelligent tool and process design. We had a machine in the 1970s. It never caught on. So did some of our competitors. We never had, up until recently, the high rotational speed direct drive, highly stiff torque motors that we have available in the market today. And also, we did not have the ability to manufacture the tool with these 5-axis grinding machines to what we need for the complex geometry. Here you can see what I just described, which is the highly negative rake angle with the resultant cutting speed from 2 vectors, and the cross axis angle. And basically, that spindle speed is generating the cutting speed. And then you can see if you have a big infeed depth and let's say less passes, so you only take most of the material in one pass, you have an extreme high negative rake angle, and the tool stability or tool life is terrible. So typically we go with these small infeed strategies, multiple cuts, and then that improves the rake angle and the tool life situation. So yes, knowing that, what we could say is when we first saw these machines introduced to the market in the year 2007, or let's say reintroduced to the market in the year 2007, that some parts, let's say some work pieces, you would get a tool life 50 pieces, okay, then maybe 60 pieces, 70 pieces, 40 pieces, somehow stable. And then along comes a batch of stuff and you get maybe 2 parts and then the cutter blows up. So that was very inconsistent and not really robust enough for high performance cutting. So what we did at Liebherr is, since we own a cutting tool facility, our factory in Italy and also in Ettlingen, Germany, we started with a complete simulation of the cutting tool with the process, knowing that at a specific cross axis angle, a specific cutting speed and feed rate, the cutting tool should be defined. So that's how we started with it, to really understand the complete chip cutting formation with our own simulation software. And that is really how we design the cutting tools today. So we know the complete process. We don't change cross-axis angle on the process. We don't change cutting speeds and feed rates. The tool really must be designed in harmony with it. And I think that's why maybe you see nowadays a lot of manufacturers with whoever has 2 spindles on their machine tool. Pinch turning, for example. You see a lot of turning machines show skiving, but do they really know where to buy the cutting tool, how to manufacture the cutting tool, and understand the process? And can they really get a repeatable, reliable process? So we at Liebherr, we can do that. We provide, we call it Skiving Cubed, the complete turnkey package. We say it's not just, let's say, an improvement over what others do, but we say it's absolutely necessary to get a stable process. And I think that's really the truth, myself looking back on it as a manufacturing engineer, having some experience with the process. And we also make PMHSS particle metal high-speed steel tools and carbide tools. And we choose, yes, where the applications are needed, because as I said, we manufacture these tools at our own facilities. So therefore, we can really offer to our customers, yes, a complete understanding of the gear cutting process, as we do in hobbing, shaping, gear grinding, gear inspection. We can also do the same with skiving. Okay, and another important topic, or let's say innovation, which has come along in the recent years, is chamfering of gear teeth. Why do we chamfer gear teeth? So if you look on this photo, you can see after hobbing, we have a gross burr, and we can deburr that. Normally that's done with a rough deburring disc in the hobbing operation. But what we're talking about is chamfering the ends of the gear teeth. So this chamfer along the top flank of the tooth, that's done in the hob cutter. That's called a semi-topping hob cutting process. That's not what we're talking about. This chamfer here, shown in the tip of the tooth, that's done with the turning operation. We're talking about in the gear flanks all the way through the root. That's specifically the place where we're talking about chamfering. Yeah, so we do it to prevent handling damage, so workpieces don't clank together. And we also do it for, yeah, let's say gear design reasons, and especially designing for different gear cutting processes like honing or gear grinding afterwards. We had many ways at Liebherr to do the chamfering process. Shown on the left is, let's say, in parallel to our hobbing process. So when we were hobbing the gear, we were also doing these milling operations on the side of the machine tool, so the cycle time comes along for free. Same with roll press chamfering. The disadvantages of these first two shown on the left are the finicky setup of the milling pins. It takes a long time to change over and for the operator to get a consistent chamfer. Also, you get terrible needle chips, which are really difficult for operators to handle, almost a safety hazard. Press chamfering, that's really plastically pushing material around, and then we clip it off. That's also not so great for the gear quality at the ends of the gear tooth. Sometimes we get raised material there. And also for honing operations or subsequent gear finishing operations, it can be detrimental to the tool life of those processes. So we came up with, in the year 2005, together with the company LMT Fedi, this chamfer cut process, which we shift over on the hob cutter and we actually cut the tooth. Here you can see what I was describing, where we had the chamfering units for the milling pins and the deburring. This is what the chamfer cut process looks like. You can see it here when we chamfer on our hobbing machine. So this is the Liebherr LC180 gear hobbing machine. You will see it cutting a process dry. Incidentally, Liebherr invented dry cutting in the year 1993, so that's what's going to be shown here. Here we don't switch off the fluid. This is really cutting dry. Not so new. Everybody knows about these coatings and everything nowadays, but we pioneered that in the year 93. So we hob the workpiece. That's what generating cutting looks like for hobbing. Again, the tool is perpendicular to the workpiece. It's like a worm to worm wheel relationship. And there you see the chip. Right, and it'll index 90 degrees with our automatic loader, and it'll go to hob the next workpiece. And then simultaneously, we have this cutting process that we pioneered in 2005, this chamfer cut. What we've done putting it on the 4-station ring loader for automation is the cycle time comes along for free. So now we're really cutting it. We're not pressing the chamfer in. We don't have these finicky setups. It's got a very short setup time and an extremely long tool life. Very small cutting forces. We're really cutting the material out with a, let's call it, continuous milling process. So here you can see we find the teeth with an inductive sensor. And then we shift over, chamfer the top, chamfer the bottom. There you're going to see the top being chamfered. And then the bottom of the tooth being chamfered. Good. That's what the process looks like done in parallel. And here you can see it's completely cut in a single contour with those cutting tools. Cutting tools have to be specifically designed for a workpiece application, but you get tremendous tool life when the subsequent finishing processes, and you get a completely uniform chamfer, which is becoming extremely important in e-mobility, but also aerospace too, where the chamfers are specifically defined. And as I said, the changeover is straightforward and easy, simple for the operator. No finicky setups, reduction in changeover time. You put the cutter on, which is, let's say, air-proofed, with you can only put it on keyed in one direction, and then you plug the data into the control and go. You can also make, it's completely NC, corrections, so you can change the chamfer width. Instead of these finicky pins that had to be set up and adjusted as tool wear occurred. Very simple corrections. And then we also, in the recent years, started with a standalone chamfering machine, and that's what's shown here. In case you don't want to buy it with the hobbing, maybe you have a customer has a fleet of hobbing machines from one of our competitors, for example, and then you can just add the chamfering process in the process chain. Right. Good. And now a little outlook for what we think is going on. For sure, e-mobility is one of the future demands we're faced. A lot of our innovations on generating grinding have already been used in production and are being used for passenger cars for e-drive. The twist-free, the generated end relief, sometimes with polishing, as I mentioned. We see a real future for the dressable CBN. Tooth chamfering has become really important in nearly all of our discussions with customers in North America. So the idea is that you can engineer the chamfer to really control the face width of the workpiece and the design critical nature, even in aerospace. But we also have a stable process and a quick changeover time and reliable, easy to handle for the operator. Also important in North America specifically, yes, in Mexico, sometimes in Asia, we have really customers who don't need the experience. You just switch out the tools and go. It's also done in parallel nowadays. We don't have to reduce the hob length like we had to use in 2005 when we introduced it. And it can be chosen individually, so you really design the cutter around the workpiece. And then skiving, we see a really increased demand. Yes, compared to shaping, it's a much faster cycle time for production of internal gears, but also for e-drive, there's these double gears where you sometimes have collision situations, and skiving is a real alternative to shaping and faster in that case. And the only other thing to mention, like I said at the beginning of the presentation, we're here. I mean, Liebherr will be here as long as we make gears for our own uses at Liebherr. So we're not going anywhere. We're a very reliable partner, and we're pleased to work at all of our customers in North America. Just by reference, there's over 2,000 gear machines from Liebherr running in this continent in North America. So yes, that's the presentation I have. I really appreciate the audience and the chance to present today with the VDW. I hope that I see some questions coming, and I will turn it over now to Mr. Boglin and see if there's any yes, chat questions or others.
Exactly. Thank you very much, Scott, up to this point for your presentation. Yep. We're now coming to the Q&A session. This means if you have any questions, just type them in the question box and Scott will be happy to answer them. I cannot see any open questions yet, but we will just wait a couple of moments.
Okay,
to give
good.
You the opportunity. So
okay.
If you see, all right, yeah, I see the first one popping up.
I see a question coming. Right, one person is asking about our gear metrology or gear inspection. If we have a so-called feedback or closed loop inspection to our gear cutting machines. That's a good question. The answer is yes. As a matter of fact, that's one of the reasons why we purchased this metrology division of a company in Germany a few years ago. We see also a future trend of as let's say lights out production or closed loop inspection of gears. So you can take a gear that you hobbed or shaped, and we can, yes, make an inspection of the workpiece and feed back the data to the machine tool and make corrections. Of course, this is prompted with some safety. The operator has to acknowledge such a correction so that there's no, mistakes made. But we call that LHT connect on our platform between the gear metrology machines and the gear cutting machines. And we use a German standard or norm from the VDW. It's called Gear Data Exchange. So we use the Gear Data Exchange format, which is a known standard. So you could even take the Liebherr inspection machine and work with one of our competitors' machines if they're working in the Gear Data Exchange standard. That's an absolute fit to our machine tools.
All right, thanks for this answer. And again, if you have any more questions, just type them in the question box.
Okay, another question's coming about the Industry 4.0 or Internet of Things and how Liebherr sees this trend developing. Yes, of course, that's another topic for the future. Most all machine tool manufacturers have this presented from our customers. And yes, we do have a platform for that. Again, we work in that same structure like we do the Gear Data Exchange to our metrology machines. It's called LH Connect. But here we're also working with, yes, the other CAN softwares which are available to monitor machine tools like MT Connect and others. So I'd have to put you in contact with our colleagues in Germany. Okay, I have another question coming. Does your R&D continue to occur in Germany exclusively, or does it occur in other countries? The answer is pretty straightforward: in Germany. So our research and development, yes, we have complete design capabilities at our parent location. And we also have testing. So we have a complete test center where we have basically one of each machine tool that we produce, and we do customer trials and we do product development. But that's all in Germany. We do in North America at our facility here in Michigan. We do have a similar, let's say, sister testing area where we're doing customer trials, but I would say this is exclusively customer trials and not product development or R&D. So any scientific research we do or any product development stuff, that's done at our parent or in our factory in Kempten, Germany.
Okay,
Good.
so I think that's it for the open questions right now. I cannot see any more questions coming in. So Scott, you're welcome to address some final words to the audience and say goodbye.
No, just like I said, pleased to have the opportunity, and thank you for the VDW for the chance to present. I think it's a nice format you're doing in the case of the pandemic, that we can at least meet, but hopefully next time in person.